You know what a porcupine is? Hmm? Yes? No? No? What is it called? We, we call it Mullambanri. So this was the theorem stated the other day, right? That's what that theorem says. So what does the theorem say? There is no non-vanishing continuous vector field on the sphere, tangent vector field. Okay. So what that means is, so tangent vector fields are vectors tangent to the surface, right, at every point. So if you want, you think of a head for the sphere there. Ah. A ball there. Uh, so surface of the sphere, think of the surface of the head. So tangent vector fields, when you comb your hair, so lies along the surface of the sphere, right? So you can't get such a thing uniformly. So there will be some sway there somewhere, okay? So without that, you can't comb smoothly. So that's what the theorem says. This is just a fancy way of stating that, okay? So, of course, this is only true for even dimensional spheres. Odd dimensional spheres always have. So if your head was a three-dimensional ball, then you can comb smoothly like that. So the Milner's paper of Milner referred to the lecture there, and the afternoon lecture, okay, called elementary proof of an analytical proof of the Harry-Ball theorem and the Brouwer fixed point theorem. I think that was the title. So you can find it in the monthly, American Mathematical Monthly. I forgot the year now. Maybe I can find out and tell you. So, of course, this is result in topology, but his proof is differential. He proves it first for the smooth case and then approximates it. By approximation, you get it for continuous vector field also. So if you want, you can think of this as something in differential topology. There is a nice little book by Milner on this topology from a differentiable viewpoint. very small book of lecture notes that Milner gave at some place, University of Virginia, or something like that. So any book on differential topology is essentially based on Milner's book there. An amplification, perhaps, of the book of Milner. Milner writes beautifully, so all his books and papers are very nice to read. Of course, he is the master on the subject of differential topology. The theorem itself, I think, is due to Heinz Hopf. But you find a very nice proof due to Milner there, and subsequent elaborations on Milner's proof you can find in many places. There is a book on differential topology. One of the standard books is a book on differential topology by Guillemin and Pollack, which is essentially an amplification of Milner's little lecture notes there. So this is just a remark on something that was discussed last time. Vector fields on spheres is a very important study about vector fields. So we'll now get back to what we had been doing. So what were we doing last? We defined the tangent space, right? And we gave some examples of surfaces, and then we defined the tangent space and said that the tangent space is the orthogonal complement of the gradient, right? That was the theorem. So these proofs of three results that I have already mentioned, I have written down for you here. I'll possibly explain a few things here and there, and then pass on. Okay? Yeah. So this is the theorem, right, which expresses the tangent space as the orthogonal complement of the gradient vector field there. So you will have to prove. So you want to prove equality of these two. So you have to prove two inclusions, containment each way. So this way is just chain rule, right? So if you take any vector there, it's going to be this form. So differentiate this, we'll get this. Okay, so which shows that the tangent vector is orthogonal to the gradient at that point. So one inclusion is just chain rule. The other inclusion needs something on vector fields and integral curves of vector fields that you have discussed. So the reverse inclusion, so you take a vector in the orthogonal complement. So what do you have to do? You have to find a vector which fits this vector at that point P as a tangent. So what you do is, so you are starting with the vector V. So start with the vector field which is constant, that vector at every point. So V is the vector coming from this vector field there. The tangent vector has two parts, the point and the vector. So take that vector at every point, you look at the vector field given by this. So the constant vector field, and then so what you do is you project that on this component there. So subtract. So this is your x. So subtract from x this component of that in this direction. So call it y. So at P, this is 0. Okay, you are starting with something which is orthogonal to this. So this part is 0 at q equal to p. So this term vanishes at p. So you get that y is same as x at p and same as v, that is the vector that you started with. So now you use the theorem. So you have a vector field y. So you fit an integral curve to that vector field passing through the point p. So if you take that vector, that curve, integral curve alpha to the vector field y passing through the point p, you can verify that that fits the bill. Okay? So if you differentiate this, you will get 0, and therefore f is a constant, f of alpha t is a constant. So what do you have to show? You have a curve, all right, but you have to show that the curve lies on your surface. Okay? So which means that you have to show that f of alpha t is a constant. So surface S is the level set at the point at C, okay, at the level C. So you have to show that f of alpha t is a constant. So differentiate this, you will get 0. So it is a constant. So it's same as the value at 0, but the value at 0 is p. That's it. So the essential ingredient in the proof is the existence of integral curves to a given vector field. Okay? That's what we have made use of. So that's essentially the proof there. You see, I told you that surfaces generally can be described in two different ways. One as a level surface and the other as a parametrized surface. Right? At each point you have a patch going to the Rn and so on. Right? So this tells you that if you start with an n surface according to our definition, which is a level surface, okay? So around each point you have a coordinate patch or a parametrized patch. So this is an easy application of the inverse function theorem. So this is a statement. So take any point on the surface, then there is a patch around the point and a map which gives you the coordinate patch around that point. Right? So there is a smooth, there is a neighborhood, there is a smooth map, so that this neighborhood is mapped onto the neighborhood of the point on the surface. So V is a neighborhood in the Euclidean space. When you intersect it with the surface, we get a neighborhood on the surface. Right? So you want, if you want a coordinate patch, there is a restriction on the, there is a condition on the map. The Jacobian or the derivative of the map at that point should have rank n, should have full rank. Okay? The Jacobian has rank n. So what you do is, so you are starting with this. So this is the surface given. So this is a condition. The gradient is non-zero at every point. So what you are doing here is to essentially, so this also can actually be expressed as saying that in a neighborhood of the point, this surface is actually a graph. Right? If you take a function f and look at its graph in R3, right? Function of x and y, look at it in R3 as a graph of the function in R3. This is how you represent it. That means, so what are the points here? At any point x, y, in whatever domain where f is defined, the z coordinate is given by f of x, y. Any surface which is got as a graph is also a level surface, right? So this you can write as z minus fxy equal to 0. So if you call z minus fxy or as g, for example, so g x y z equal to 0. That's a level surface. So anything which is expressed as a graph is automatically a level surface. So that's what we have here, right? So x1, x2, xn, the last coordinate is a function of the earlier one. So this is nothing but the graph of the function f. Okay. So the assumption is that the gradient is non-zero at the point P. Okay. So which means at least one of the partial derivatives, del 1, del 2, del n plus 1, is non-zero at the point P. So without loss of generality, assume that the n plus first partial derivative is non-zero. Otherwise, you can. It's just a matter of labeling. Okay. I mean, the convenience with this choice is that when you write the Jacobian, you will get a nice looking. Instead of this lying somewhere in the middle, it will go to the one end of the matrix there. So the Jacobian will look like this. Jacobian matrix will look like this, right? So Jacobian of this. That's why I have written this way. So the Jacobian determinant, therefore, is going to be, so on the diagonal you are going to have 1, 1, 1, 1, del n plus 1p. This is triangular matrix. Okay. So the determinant is going to be just the partial derivative del n plus 1 f at p. So by assumption it is non-zero. So which means this Jacobian is non-singular, and therefore you can invoke the inverse function theorem to conclude that there is some neighborhood where psi is a diffeomorphism, right? So psi is a local diffeomorphism around that point. So give the names to those neighborhoods and all that. So here again you can make a small reduction. In Rn or Rn plus 1, whatever things occurring there, products of intervals form basic open sets, right? Any neighborhood of a point will contain a neighborhood of the form a1 b1 cross a2 b2, etc. Right? So these products of intervals form basic open sets. So any neighborhood of a point P will contain a neighborhood of this type. So you can go to a smaller neighborhood, restrict your diffeomorphism to the smaller neighborhood and its image. So in other words, you can, without loss of generality, you can assume that your neighborhood that you get is of this form. Okay? And then if you define phi like this, this is the required parametrization of the surface. You put the last coordinate to be the constant that you have from the definition of the surface, the level at which you have the level surface. Okay? So psi restricted to whatever this is, W inverse at y1, y2, yn, the last coordinate, put it as C. Then, so this gives the sought after parametrized n surface patch around P. So the theorem gives you something, a patch around each point. So the conclusion therefore is you can cover the surface with patches like this, parametrized patches. That's what I have written there. Okay. Of course, according to your book, a parametrized surface is just one patch of what I have. So that's why I have called it as a parametrized surface patch rather than a surface. Okay. So your book calls it as a parametrized n surface. So I'm just calling it as a parametrized n surface. So all these patches together cover your n surface. So the definition of a surface as a level surface, as a level set, implies that it is a parametrized surface in this sense, covered by parametrized surface patches. Okay, so just an application of the inverse function theorem. The other one, I will not go through this proof. Okay, it's again an application of the inverse function theorem. It's in the converse direction. It says that if you have a parametrized patch, then locally it is an n surface in our definition, only locally, right? So if you start with a parametrized surface patch, so at every point there is a neighborhood on which your parametrized surface is got as a level set of a suitable smooth function. That's what this says. So every parametrized n surface in Rn plus 1 is locally, this is of course important, you can't get globally. So here you also have to use your orientation and all that. But again, essentially, it's application of the inverse function theorem. You take the orientation, apply a suitable, take a suitable function here, apply the inverse function theorem there. Because, so you have to, a surface patch is from Rn to Rn plus 1, right? And open set in Rn to Rn plus 1. So, but if you want to apply the inverse function theorem, you have to get n plus 1 to n plus 1, right? Rn plus 1 to Rn plus 1. So that's why you have to define a new function. So this is in Rn plus 1. So you apply the inverse function theorem to that function there. So this is the function which comes from the normal vector field or the orientation of vector field. So I will not run through the proof. It's there. I have written down everything. Okay. So any level surface is a parametrized surface, and any parametrized surface is a level surface. Everything happening locally only. Okay, so tangent vectors and so I mean when you want to differentiate or take a tangent vector, you only work at the local level, right? So whatever you want to do locally, it doesn't matter whether you start with a level surface or a parametrized surface. Okay. Okay, so let us look at some more examples. The other day, so we computed tangent space at the identity to SL2R, right? SLNR in general. Is what we saw that day. Okay, so this is essentially only example that you'll see, which is not a two surface in R3. Right? So this is, even when you take n equal to 2, you are going to get a 3 surface in R4. So most of the other examples that you are going to look at are all two-dimensional surfaces in R3. Of course, this example is important for various reasons, which we will not go into right now. Of course, one of the easy ways to compute the tangent space in general is to use that theorem as the orthogonal complement of the gradient. When you express the surface as a level surface, that is always easy to do. So let us look at examples. So maybe this is the first example. So let us look at the simplest of two surfaces. Of course, equally works for n planes in Rn plus 1, but let's just take planes in R3, right? Equal to 0 or C, doesn't matter, okay? Equal to constant you can take if you want. So what is gradient? So this is your f now. What? A, B, C, right? Partial derivatives. Partial with respect to x, partial with respect to y, partial with respect to z. So to get an orientation, you have to normalize this. So I don't like to put an arrow there, but anyway, so huh? Oh, delta equal to, okay, at any point. Del f at xyz for any xyz is ABC. So the normalized gradient. So this is going to be 1 over of course not all of them are 0 because otherwise you don't have any equation there. But anyway, so this is not what you are looking for. This is not relevant to us right now. So we are trying to look at the tangent spaces, so which are the orthogonal complements of this, right? So what is the orthogonal complement of this at any point? The gradient is a constant. So what is the orthogonal complement of this vector there in R3? It is just the plane itself, right? The plane that we started with. XYZ is orthogonal to ABC, means x plus by plus az equal to 0. So the tangent plane is itself. Of course, normal is a constant in this case because we have at any point on the plane that you have the normal in the same direction. Let's look at the sphere. Again, you can write down the n sphere if you want. So this is your so let's take some point, let's say E3 for example. E3 is 0, 0, 1. So what is the tangent, which is a point on the sphere, okay? 0, 0, 1 is a point on the sphere. So what is the tangent space at that point? So this is right? So what is this? 0, 0, 1. So yeah, so this is the, just gives the x-axis, I mean z-axis. The orthogonal complement is the xy plane. What is the equation of the xy plane? So this is a hyperbolic paraboloid. So give me some point on this. Let's try to calculate tangent space at some point. Or on 0, 1 is the point? Yeah, I suppose. So take any one of these points and find out what the tangent space is. So what is the gradient? So I write this as, take everything to one side. So z minus x square plus y square equal to 0. So take these points and see what the orthogonal complement is. Hmm? Origin also is a point, of course. Yeah, sure. See, the last coordinate is always 1, so it's not going to be 0 anyway for the gradient. So take this, for example. What is the tangent space at this point? Call this as S. So what do we get? 1, 0, 1. So minus 2. So this is the plane. What is the equation of the tangent plane? Orthogonal to minus 2, 0, 1. So z equal to 2x. Okay, let's look at just one more example. One of the familiar. Let's take a hyperboloid. Or the other one. This is what? This is one sheeted or two sheeted? two-sheeted. Okay, so take some point on this. Hmm? Yeah, calculate the tangent space, whatever point you are taking. Hmm? Then, at what point did you calculate? 1, 0, 0. So what is the tangent space? Huh? Why is that plane? Give me one point other than 1, 0, 0 on the surface. For example, for in a t, so this is a point on the surface, right? Cosine hyperbolic, cosine, sine hyperbolic. So this gives you a whole. So this gives you a curve on the surface, right? Actually, parameterized curve on the surface. So this I have mentioned. I'm repeating again. So when you geometrically, the tangent space at that point is going to be plane like that, right? But this, if this is P, this is S, what is TPS in the picture? The same plane, but translated to pass through the origin, right? Parallel to this, but passing through the origin instead of just shifted to 0 from the point P. So this, I think I use term like this is the geometric tangent plane, and this is the tangent plane that you have. So when you think of pictures, you must think of the tangent plane like this, right? When you actually work with the tangent space, you have to think of this. So they just, looking at the plane as lying in TPRN rather than Rn itself, right? So this is P cross Rn. So the origin is itself at P there. So for this is going to be a subspace, vector subspace of this vector space. All right, so now we come to the all important so for this need orientation, so S is going to be n surface in Rn plus 1 oriented. We usually also assume connected. Otherwise, we are going to look at the connected components. Each connected component will be a oriented surface. So we have an orientation given by the unit normal vector field. So this gives you the vector at the point P. Okay. Of course, this is either the gradient, normalized gradient, or negative of the normalized gradient, plus or minus so first you have to fix your choice. So either take that or minus, plus or minus, fix it. Okay. So what does this n do? Let's forget this. Let's look at this. For each p on the surface, np is a unit vector, right? N is a unit normal vector field. Okay. So norm of this is 1. Either write this or this, it's okay. The norm is 1. So for each point P on the surface, n gives you a unit vector. So geometrically, what is happening? So your surface you have, okay, like this, and you have normal at some point. So what is this now? The same vector so the point on the unit sphere, right? So this is the point on the unit sphere. So if you want to think of that as a vector, so this is the vector. Okay, so this is normal to the surface, and that gives you this vector here on the unit sphere. So what does n do? This is the point P. At each P on the sphere, you have a normal, unit normal. So you put it here, arrow head, the point on the unit sphere. So n gives you map from the surface S to the unit sphere. Okay, well, I don't know. Yeah, R, right, like that. So some special R, right? So if you want, you can put some special S there. எப்படி வருது டெக்கில் எப்படி வரும் அது எஸ்ங்கிறது I don't know. Anyway, okay. So S2 is a unit. Well, of course, in general, we have Sn. If you have an n surface, you will end up in Sn. So this is the setting. The function n
of x. Sorry. So this map is a crucial one in what we are going to study hereafter. Okay, in defining the curvature of the surface. The most important quantity, geometric object on a surface is the curvature, or the Gaussian curvature as it's called. So that is going to be defined in terms of this Gauss map.
Okay, so this is a Gauss map, which is a smooth map from the surface to the unit sphere of appropriate dimension there.